Welcome back. My name is Renee Clary, and today we will investigate another geologic process that has modified the Earth through time with erosion, transportation, and deposition. Today's topic is wind and desert regions. It's become increasingly popular in the news as scientists investigate the possibility of changes, increased desertification with climate change. Let's get started. Why are we studying wind? Well, again, climate change can affect various Earth systems, and increased desertification may occur with climate changes. Wind is a geologic agent, and as we've mentioned several times in several of the video lectures, wind as a geologic agent then is capable of eroding, transporting, and depositing. All geologic agents can do that. Wind, like running water, also sorts very, very well, but sorting isn't necessarily a process that all geologic agents do. Let's start first with erosion. Wind can erode in two ways. It can erode through abrasion and deflation. By abrasion, we're looking at siltation, or the process in which a sand grain is lifted up into the air column and then will fall back down as the energy decreases in the air. This usually happens to about 1 meter. So saltating sand will etch, pit, and polish rock surfaces and any other surface in its way. A ventifact is a stone that has been abraded by the wind, and we'll look at that in just a second. A yardang is an elongated ridge, a desert feature, and yardangs form by differential erosion. Here we see some fairly strange formations. The rock type here is limestone, and it is in Deserto Libico in Egypt. And what has happened here is that the saltating sand has eroded the lower part of that limestone. So you can see that it is sort of a little pillar-like structure, and the bottom part of it has been more greatly eroded and polished and pitted by the saltating sand than the upper part of it. Sand can only saltate about 1 meter above the surface. The way that ventifacts form is through abrasion by sand. Here on the left-hand diagram, you will see wind blowing from the left. Note the direction of the arrow. So the sand is saltated by the wind, and it will abrade the exposed side of the rock, the left side of the rock, creating a flat surface and sharp edges. Now, how does that differ from river action or water action? Right, okay, so water tends to produce more rounded stones or gravel. So when wind is the geologic agent, we tend to get sharp edges because the side that's exposed to the upwind direction will be eroded and abraded. But the downwind direction is fairly protected. Now, of course, that doesn't mean that the wind can't shift, because it can't. The ventifacts on the right in the photograph are from Death Valley in California. Note their sharp edges. More ventifacts. And even more. This is the first image of Mars from the Spirit, taken in January of 2004. Geologists got very excited about this because here we have some great ventifacts. It looks like a very arid, comparable environment to that of Earth. How about a yardang? Here's one in the Roman playa deposits in Egypt. It's an erosional feature, differential erosion. Okay, in addition to abrasion, wind will also erode by deflation, and by deflation we simply mean the removal of the loose sediment, and this results in a lower ground level. In other words, we're taking away the loose particles, and as a result we're removing part of the surface, so we're lowering the ground level through deflation. we end up with differential erosion, seeing some deflation hollows, or what are known as blowouts, and these are shallow depressions in which the looser sediments have been taken away. Desert pavement can result, and this occurs after the loose sediment is picked up and transported out of the vicinity by the wind. The coarser particles, the particles that are bigger and too heavy to be moved by the wind, are remaining. And what happens is that these coarser particles then form a mosaic on the surface, the desert surface, and they actually protect against further erosion because they are protecting the finer sediments underneath them. So the finer sediments are kept away from the blowing action of the wind, and the desert pavement, this coarse particle surface, this mosaic, will protect those finer sediments below. Here we see a deflation hollow. It's formed between two sand dunes. This is in Death Valley, California. Great place to visit. It's hot even in October, though. I can testify to that. And this will show you how deflation results. Note that the wind in this diagram is blowing from the left, and it will pick up the finer sediments, the finer particles. It can carry the silt and clay, but the sand is saltated. Silt and clay can be carried in suspension, and we'll look at that in a little more detail in just a minute. So the finer sediments are taken away from the area, and what remains are the coarser sediments, and these form sort of a mosaic that protect the finer sediments below. This is desert pavement. Here is a photograph of desert pavement in the Mojave Desert in California. You see coarse rocks and the coarser particles on the surface, but below the surface we do have finer particles that are being protected. Well, how do we know that? Well, on a field course, if you take a hoe along and you remove that upper coarse layer, you can see the finer particles underneath. So what's going to happen now that we disrupted that surface? Well, again, the finer sediments will be taken away that are exposed. The wind will carry them away, and a new layer of desert pavement will form as the coarse particles accumulate. Transportation of sediments. Wind is not as an effective geologic agent as running water, and of course ice is the most powerful geologic agent that we will investigate this semester. Wind, however, can transport sediments. It can transport sediments as a suspended load and as a bed load. Now, the reason that wind cannot carry large particles in suspension is because the density of wind is low and it can't support those heavier particles. Remember, if you're looking at water, sand-sized particles can be carried in suspension dependent upon the energy of the water. And this is translated from velocity of the water. So with wind, even though it may blow at a much higher velocity than running water, it doesn't have the density of water, and therefore it can't have larger particles in suspension the way that water does. Now, sometimes, of course, if we have very, very strong winds, think tornado or hurricane, for instance, bigger particles can be carried a short distance. But in general, when we're looking at wind, only the finer particles can be transported in suspension. So we're looking at clay and silt that can be transported in suspension as part of the suspended load. Wind cannot carry the larger particles. Here we see a very old photograph of a dust storm in Kansas. This was during the Dust Bowl years, before farmers practiced sustainable agriculture and unfortunately weren't aware of crop rotation and the necessity of rotating crops in order to replenish the nutrients in the soil. They also didn't plant trees as windbreaks, and unfortunately during the Dust Bowl years many areas of formerly planted soils were caught up in sort of a whirlwind and blown away. Wind can also transport as bedload, and this is where we're going to see the movement of sand. the sediment, the sand-sized sediment, is transported by saltation. So what happens here is that it's going to sort of bounce along the surface as it moves downwind. The energy of the wind will be imparted to the sand, which will then rise about a meter above the surface until the energy, it's lost its energy, and then it falls back down to earth because of gravity. So anytime this saltating sand encounters a surface, it will abrade, erode, and pit that surface, and it only causes abrasion about a meter above the surface. Transportation can also be by rolling or sliding these larger particles along the surface as well. But in suspension, only the finer stuff, the clay and the silt size, can be carried. Okay, this diagram shows a wind again from the left. It must be a prevalent westerly, and it picks up the loose sand, and you can see the pattern that these individual sand grains take through saltation. They're lifted up by the energy, and they rise maybe about a meter above the surface, and then gravity will, force their return back to earth. What about deposition? Well, we can look at two different types of deposits made by wind. The first is probably the most familiar to you. That is a dune, and we'll look at the different types of dunes first. The second type of deposit is what I call the famous L word in geology. If you ask 5 different geologists, you'll probably get 5 different pronunciations. I'm going to go with lus. That's the way that I pronounce it, but I've also heard lus, lus, lus. Very strange pronunciations of the L word. Let's look first at dunes, though. Dunes are an accumulation of sand, and they are near the source of the sand. We don't see sand dunes forming very, very distant from the source. Dunes form when wind flows around an obstruction. So, for example, here we have the direction of wind flow coming from the left. And note what happens when the wind flows around that obstruction. You have wind shadows created both in front of the obstruction and behind the obstruction. So with the lower velocity and the wind shadows, we tend to see deposition both in front of the obstacle and behind the obstacle. The bottom view shows you a profile of what happens with the accumulation of sand. So, as the sand is moved through saltation, it's not carried in suspension, but as it is moved via saltation or by rolling and sliding, it will blow up the windward side, and then the sand will slide down what's called the leeward side, and it forms a steep, large-scale crossbed. Let me show you how that works. Okay, note the difference between the windward side of the dune, and that's off to the left. The wind moves the sand by saltation, and at the crest or the top of that wave, the sand slips down a steeper leeward slope when the angle of repose for sand is exceeded. So the dune will actually migrate over time because the sand will saltate or slide or roll up to the crest, and then we have an angle of repose that is exceeded, and the sand will slip down that leeward slope, and over time we see a migration of a dune. So with these sand dunes in Death Valley, California, can you tell the prevalent wind direction? Look for the windward side, which should be less steep of a slope, and the leeward side, which should be steeper. Okay? So if you said from the left, you are correct. The leeward side is the steeper side, and that is on the right of each of these dunes. Okay? Now, ancient sand dunes and the crossbedding can be preserved as well. This crossbedding is exposed in Zion National Park in Utah. What is the prevailing wind direction? Okay, this was a trick question because the wind direction changed over the time of the formation of these various crossbeds. You know, we have one there that's fairly obvious, and then we have, you know, a different direction. So that's why our crossbeds that are preserved in the rock are pointing in slightly different directions. We did have a shift of the prevailing winds. There's a dune. What's the wind direction? We're keeping our trend here. It's from the left. The leeward side is to the right of the dune. Okay, well, there are different types of dunes, and we're going to investigate. There are 4 main types, and then there's an extra one that we will discuss as well, the star dune. A Barkhan dune is a crescent-shaped dune. It will be one of 2 crescent-shaped dunes you encounter in this class. But with a Barkhan dune, the formation occurs in areas where there is very little vegetation and a limited sand supply. The tips of the crescent point downwind. Okay? So with a Barkhan, the tips are pointing downwind. Diagrammatically, this is what a Barkhan dune looks like. Note the wind direction is sort of from the lower left corner of your screen, and the tips of that crescent are pointing downwind. Here we have Barkhan dunes in the Salton Sea, California. What's the wind direction? From the left. The tips of the crescent point downwind. Okay, how about this one? This is up close and personal again, and there you see it, it's from the left. Longitudinal dunes, or scythe dunes, form as ridges that are parallel to the wind, and these also form in areas like Barkhans with a very limited sand supply, but with a longitudinal dune we have winds converging from different directions. They may be quite large. Here is a diagrammatic representation of a longitudinal dune. Again, we have winds converging. These are longitudinal dunes that formed in the Gibson Desert of Australia. Those blue areas, by the way, are shallow pools of water, and the darker areas are the remains of fires that the Aborigines set. And they do this to encourage spring grass growth. What's the direction of the wind? There you go. Okay, so we've done Barkhan, we've done longitudinal. What about transverse dunes? Transverse dunes are perpendicular to the prevailing wind, so they're at 90-degree angles to the prevailing wind. Now, the difference between a longitudinal and a transverse, so that you can tell, you know, here we have these ridges of sand in both a longitudinal and a transverse. So how do we know which is which? Well, a transverse forms where there is abundant sand supply. And because they often take a little bit of an undulation, they can look like waves. So we see sand seas of transverse dunes. They form in areas where there is little vegetation. And we can also see a Barkhanoid dune. This is an intermediate between a transverse and a Barkhan dune. Barkhanoid dunes tend to form at the edge of the sand field where the supply becomes more limited. Remember, Barkhan dunes, those crescent-shaped, form in a limited sand supply with little vegetation. A transverse has an abundant sand supply, but as you reach the end of the sand field and the sand supply is more limited, you can see sort of a movement to a Barkhanoid dune, and then Barkhan at the very edge of the sand field. Here is a transverse dune. Note that it's at 90 degrees to the direction of the wind. Here are transverse dunes at Great Sand Dunes National Monument in Colorado. What's the wind direction? Remember, it's going to be at 90 degrees to the ridges. You should also be able to pick out that leeward face, the steeper face, that is downwind. And there we go. The direction of the wind is from the lower left of the photograph. Here are some Barkanoid dunes, and these tend to form toward the edge of the sand field. Look at the tips of the crescent. What is the prevailing wind direction? From the upper left. The last of the major types of dunes is a parabolic dune. These form typically in coastal areas because the vegetation that is present will anchor down the tips of the dune, and the tips are actually going to point upwind, totally opposite from a barchan. So the tips point upwind, and what's happened is that although the vegetation has anchored down the tips, there tends to be a blowout in the middle of the dune. These typically form in coastal areas. Diagrammatically, there is a parabolic dune. Notice the direction of the wind, primarily from the bottom of your screen. Vegetation will anchor down the tips, and a blowout occurs in the middle. So the formation of these is actually opposite to the barchan because the tips are pointing in an upwind direction for a parabolic. This parabolic dune developed along Lake Michigan. So what's the wind direction? You can see the blowout there and the tips. There's the wind direction. And lastly, we're going to talk about a star dune. This isn't considered one of the four main types. The four main types again are barchan, which is crescent, a longitudinal, which is parallel, a transverse, which is perpendicular to wind direction, and a parabolic, in which just opposite of the barchan the tips are in the upwind direction but anchored by vegetation. A star dune is a large dune. It can be the tallest dunes in the world, and it forms with an abundant sand supply, but the difference here, as opposed to a transverse, is that you get variable wind directions. Here we see some star dunes. Star dunes are common in the deserts of North America and Saudi Arabia. And a colleague of mine, a former colleague, took this picture of star dunes. Okay, now we're going to move on to the L word, loess. Loess, unlike a sand dune, is wind-deposited silt and clay. So we're looking at the finer particles, and how were these transported? These were transported in suspension. So as a result, loess is deposited fairly far from the source of the silt and the clay. The source can be a desert, it can be glacial outwash, wind-blown silt and clay from ancient floodplains and ancient lake beds that have now dried up. Loess accumulates in a damp area, and it's easily eroded. It will form very steep cliffs. The particles here, if you look at them microscopically, they're angular, so they hold a very steep angle. In northeast China, the thickest and most extensive loess deposits reside, although we also see deposits in the Great Plains of the United States. Here is a map of loess deposits, and again, the largest deposits are in northeast China, where the green arrow is pointing. Because of the unconsolidated nature and the angularity of the individual loess sediments, it can be excavated into caves. And here we see the Tanghua village in China. Villagers excavate and live in the caves. Notice the very steep angles that this loess maintains because of the particle angularity. Sand dunes have a much lower angle of repose before slip occurs, but loess can hold very, very steep, almost vertical shapes, but it is easily eroded. Let's shift gears a bit and talk about deserts. Deserts occur on every major continent, and they are controlled by wind circulation patterns. In general, we see desert formation prevalent at 20 to 30 degrees both north and south of the equator. We also see the formation of rain shadow deserts, and I'll show you a diagram of that in just a minute. So what's happening here? Well, solar energy heats the surface, and of course, because of the angle of the solar radiation, we have some great heating going on at the equator. So hot air is less dense. It takes up less space, so it's going to rise. And then as it rises, it cools and drops its moisture as rain. But by the time the air reaches 20 to 30 degrees latitude, it's cooler and denser, and this dry, cool air sinks, and we get warm deserts developing. So if we look here at the arid and semi-arid regions on the world, let's take a swath about 20 to 30 degrees above and below the equator. I'm actually including the equator in that. So this is the area that tends to develop deserts as a result. Rain shadow deserts can also occur, and these form when rising marine air encounters a mountain range. So the precipitation falls on the windward side of the mountains, and then the air that descends on the leeward side is warmer and drier. So this is called a rain shadow desert. What are the characteristics of deserts? You probably immediately think, well, it has to be hot. Not necessarily. The characteristic by which deserts are defined is that they are dry. They receive less than 25 centimeters of rain per year, or about 10 inches. The evaporation rates are high. There are temperature fluctuations. Little cloud cover means that the landscape can cool very dramatically at night, even if it gets very hot during the day. I used to ask my classes in Louisiana, a hot June night, let's say it's 95 degrees outside, what's it going to cool down to tonight? So if it's 95 degrees during the day, at night we might be able to expect 90. It doesn't cool down very much because of the cloud cover. Deserts don't have that luxury, so heat can escape via radiation at night. Deserts tend to have very poor soils and little vegetation. This is Organ Pipe National Monument in Arizona. Specialized desert vegetation tends to be widely spaced. It tends to be sparse. It's characterized by slow growth. There's not a lot of moisture available. The specialized vegetation, of course, develops by natural selection, and it reduces its water loss to the arid environment. And this can be done through waxy leaves or cuticles that cover the leaves. There's a shallow root system typically that collects any water that falls. This is the Namib Desert. You can see some vegetation, look in the foreground of the picture, but it is sparse. We see rock varnish forming in deserts. This is a coating of iron and manganese oxides on rocks. The iron and manganese are thought to come from windblown dust or from precipitated microorganisms' wastes. It's not from the rock itself on which the varnish forms. So what's interesting about rock varnish, humans remove the rock varnish layer in a series of designs that are called petroglyphs. And these petroglyphs that are shown in the photographs right now are found in Arizona in the top right and in New Mexico in the lower left. Mechanical weathering is dominant in deserts because there is little precipitation, little water available for chemical weathering. Temperature fluctuations and frost wedging are the most prevalent forms of mechanical weathering in deserts. Frost wedging, even though a little bit of moisture is available, if it infiltrates cracks and joints during the freezing process at night, it can do a lot of mechanical weathering. However, water is still the most effective geologic agent, even though you see a landscape that is very, very arid. When water is available, it still performs the most erosion, transportation, and deposition than wind does. Although it's infrequent, running water is responsible for most of the erosion in the landscape. For example, there is a dry or ephemeral stream, and what happens when a rain event comes? It quickly carries away a lot of sediment and does a lot of erosion and transportation. Braided streams tend to form in desert and arid environments because there is so much sediment that is being carried away by the water. It essentially chokes the channel, and the sediment is deposited, and the stream will split and then reform around the sediment. Here is an overhead view of an ephemeral desert stream. Landforms we see in the desert. Playa lakes are temporary shallow lakes that form with rain events and runoff. And when the water evaporates, we're left with what is known as a playa, a salt pan where salts have precipitated because of the evaporation, and also mud cracks are seen in playas. This playa lake is Cronies Dry Lake in the Mojave Desert of California. This photograph was taken after a rainstorm filled the lake. Once water evaporates, though, we see a playa form. Here's a photograph of a playa. It's a dry lake bed that remains after evaporation. This is Racetrack Playa in Death Valley, California. Salt deposits and ridges cover the playa in Mojave Desert. Note the crystallized salt on the surface. And we also see mud cracks. Mud cracks are common when playa lakes evaporate. Okay, besides a playa, what else is there? Alluvial fans. Alluvial fans form in desert and arid regions. This is a deposit of sediment on the desert floor as the mountain streams exit the higher topography. We see bajadas. Bajadas occur when we have many alluvial fans coming together or coalescing on the desert floor. This alluvial fan is in Death Valley, California. An ephemeral sediment-laden stream loses its velocity as it leaves the higher area, and as it loses its energy, it deposits the sediments directly on the desert floor. So this is a desert delta, if you will. A lot of sediments there. Here is a bajada, which forms from the coalescing alluvial fans. This is at the base of mountains in Death Valley, California. And here is an aerial view of a bajada. Note the different alluvial fans that are coming together or coalescing. Okay, we also have piedmonts developing in deserts. This is an erosional bedrock surface of low relief that's left after erosion by wind. Inselbergs are erosional remnants of resistant rocks. The piedmont is the erosional bedrock along the mountain front, so I can circle it on either side of that mountain front for you. That's the piedmont. This piedmont is north of Mesquite in Nevada. And here is an Inselberg. This is Ayers Rock in Australia, very famous Inselberg. Very resistant rock type 2 erosion. Buttes and mesas also form in deserts. Mesas are flat-topped erosional remnants, and buttes are isolated pillars. So the difference here is that the mesa is a bigger landform than the butte. Here's an old diagram, but one I think effectively demonstrates how these form. Note that we have a retreating cliff off to the left side of that diagram, but we have a more erosionally resistant mesa that is left in front of that retreating cliff, and it's a tabular flat top surface. And then as erosion will continue and sediments are carried away, we're left with a smaller resistant rock, flat top, that's a butte. Here are several mesas and buttes in Monument Valley National Park. Here we have two buttes, left Mitten Butte and right Mitten Butte in Monument Valley. And finally, we're going to wrap up with the causes of desertification. As you might imagine, this can be pretty darn complex, but basically we're looking at long-term climate change, and this can result, of course, from plate tectonic positions, and we can see intermediate climate changes with Milankovitch cycles. But of more concern and immediate term is the development of agriculture or human activities. When we develop agriculture in areas that are marginal, we use groundwater, but of course agriculture will accelerate erosion because we're laying bare soil surfaces that were anchored with vegetation. In arid environments, the vegetation that has developed is specialized for that environment. When humans come in and modify the landscape and plow and till and irrigate it, the plants that they are developing with agriculture are not the native plants. So this can accelerate desertification and human activities. That will conclude the lecture today on wind and deserts. It is only meant as an overview, so please, if you have any questions, please feel free to contact your instructor via email or post your questions on the discussion board. Thank you so much for joining me today, and have a great day.